So this is the second video for some special cases with gas stoichiometry problems. You should have watched the first video already, and the first video goes over how to go from a volume of a gas using ideal gas law to moles, using stoichiometry to get to moles, and go to something else. I want to show you two special cases. You can solve every problem using the concepts of that first video, but it might help you save some time if you can recognize when these special cases exist, and you can do chemical reaction stoichiometry faster. So the first special case is this. If a gas is at STP, standard temperature and pressure, either starting in STP for the problem or we end the problem in standard temperature and pressure, you can use the 22.4 liters per mole, which we looked at earlier in our gas laws unit. This is called the molar volume of a gas. And any gas at standard temperature and pressure, 0 degrees Celsius and 1 atmosphere, will occupy 22.4 liters if there's 1 mole of the gas. And we can use that ratio to speed up our problem. So I want to show you that here. This is a special case. Only if the gas is at STP. We can skip the ideal gas law. And from the ideal gas law, this number comes from the ideal gas law. We can use the molar volume of a gas to do our conversion. So it would look like this. Let's say we have ethylene. That's our C2H4. Burning in the presence of oxygen to form carbon dioxide and water vapor. At STP, so here's my indication for these problems. I might have a shortcut that works here. At STP, I need to know there's 22.4 liters occupied per 1 mole of any gas. It doesn't matter what gas it is. They want to know this. How many liters of carbon dioxide, so that's our gas here, can be formed if 85 grams of oxygen, this is also gas, but they gave us a mass here. So we're not thinking ideal gas law here. We're thinking mass to moles conversions. How many liters of carbon dioxide can be formed if 85 grams of oxygen are consumed in this reaction? So to do this problem, we want to start with our grams of oxygen. The problem is going to look like this for our conversion chart. We were given grams of oxygen. We're going to go into moles. Then we're going to go from moles of oxygen into moles of our CO2. And then from moles of CO2 into liters at STP using this ratio right here. So that's going to look like this if we write out the math. We'll take our 85 grams of O2. And I want to convert this to moles first. Anytime you want to relate two different quantities, or two different compounds, you must be in units of moles. Nothing's changed there. This is just like our previous stoichiometry problems. I'm going to go out of moles of O2 into moles of the gas that we care about, and the moles of gas we care about is the CO2. And there's 3 moles of O2 for every 2 moles of CO2. And then this is where that new ratio comes in. Because we're at STP, I can say every 1 mole, and that's going to go on the bottom, 1 mole of CO2, I'll cancel my units here, occupies 22.4 liters. And I can't stress enough that this ratio can only be used at STP. Do not try to use this at different temperatures and pressures. But this makes this problem easy. I don't have to go into ideal gas law because I can just do all my conversions all in one line. All my units cancel, and this will be my liters of CO2 that gets produced. And if you do that, your liters of CO2 comes out to 40, 39.66 repeating liters. And with sig figs, we'd round that to 40 liters of CO2 produced. So kind of a shortcut for problems that are at STP. Another shortcut that's kind of more useful are for chemical reactions where the temperature and the pressure doesn't change. So gas stoichiometry special case, this would be case number 2. If the temperature and the pressure are constant throughout the whole reaction, so this would be like a chemical reaction, maybe I'm doing it in a container, and it's just open to the air of the room. And if it's open to the air of the room, maybe our room has 1 atmosphere of pressure in it. It's just going to stay at 1 atmosphere of pressure. No matter how much gas I produce, I'm producing that gas into the room with 1 atmosphere of pressure and the same temperature, room temperature, whatever it is. If this is true, we can use volume just like a mole-to-mole ratio for gases. And I'll show you an example of this. But the reason you can use volume as a mole-to-mole ratio, if you remember back to Avogadro's principle, we looked at how every balloon, it didn't matter what gas we put in the balloon, all balloons at the same temperature and pressure occupied the same volume. And that means every one of these balloons also has the same number of moles. There's the same number of moles in this balloon as this balloon and our balloon over here. In other words, the volume and the moles are directly proportional. And if they're directly proportional, I don't have to, in my problem, convert from volume to moles, and then moles to moles, and then moles back to volume. I can just go directly from volume to volume for gas ratios, only if the temperature and pressure are constant throughout the whole chemical reaction. So I want to show you one example of this. Let's say this was our problem. Determine the volume of oxygen gas required to completely react 5 liters of hydrogen gas. This would be like a large chemical reaction with the balloon in class where we filled it up with H2 and I held the match under it and it blew up. It was exposed to the room, so I know before the chemical reaction and after the chemical reaction we have constant temperature and pressure the whole time. And that allows me to do this relationship where the moles of each is proportional to the volume of each. And so what do I want to do here? I want to write chemical reaction first. So we're going to say our chemical reaction over here. H2 gas plus O2 gas. This produces H2O. And we want to balance this, so we need 2 of these and 2 of these. And it wants to know what's the volume of oxygen gas required, so I want to figure this out. To completely react 5 liters of hydrogen gas. And here's how this works. If I'm at standard temperature or constant temperature and pressure, I can go directly from our 5 liters into our volume of our O2. Using this ratio, 2 liters of H2 gas are required for every 1 liter of O2 gas, because that would give me a 2-to-1 mole ratio, because volumes are proportional to the number of moles. So we're going to start with our 5 liters, and I just do this. 5 liters of H2. From my ratio, I can say there's 2 liters of H2 for every 1 liter of O2. And 5 divided by 2 would give me 2.5 liters of O2 needed. And this ratio only works if temperature and pressure are constant for both of these gases in the problem. And that's it. Those are your special cases.